Hey guys, so we're starting our next unit, solutions. This is topic 7 in the review book. Today our lesson is going to focus on the properties of a solution and what affects solubility. So usually the first demonstration I show you is hexane and water. So hexane and water, I can't really access them outside of the chemistry lab, but what I can show you is food coloring in water. The first thing I want to tell you is that substances with the same molecular polarity dissolve together. So you remember from bonding, we looked at polar molecules like water, where they have a big dipole and a big asymmetrical charge distribution, and nonpolar molecules like carbon dioxide, they're very symmetrical. They have a symmetrical distribution of charge. It makes them nonpolar. Because polarities are different when these types of substances interact together, you will see that they would either dissolve or not dissolve. When they're different, they won't dissolve. When they are the same, they will dissolve. So substances that are nonpolar dissolve nonpolar substances, and polar dissolves polar. We call this like dissolves like. So I want to show you the demonstration with the food coloring that I recorded earlier today. Okay, so what we have is in the regular glass, we have just water, and then in the beaker, you can see there is oil and water. And if I bring it down, hopefully you can see that defined layer of vegetable oil on top and water on the bottom. All right, so I'm just going to talk as the video plays. So what I grab is the green food coloring, and you can see in the left glass, it's just water, and in the beaker, you have the vegetable oil and water layer. So a few drops go into the water, and you can see instantly the green food coloring starts to spread out. So obviously it's very soluble in the water. It's mixing in right away without me even stirring it. And then I believe I do give it a little stir. And right away you could see it's fully dissolved. The water that's in the glass is colored green. The food coloring dissolved very easily. Now I'm going to place some food coloring into the oil. So you can see the top layer is the vegetable oil, the bottom layer is water. So these two, oil and water, they don't mix. You can see that very distinctive layer. So note what happens when the food coloring is placed into the oil. So it just beads up, falls, settles to the bottom of the oil layer, and it's not quite getting into the water because we have two distinct layers. So the behavior of the food coloring in the oil is very different from what you saw with the water, where even as another drop was just added, it instantly spreads around and spreads out. You could see over here with the oil, the food coloring is still just beaded up, not dissolving. So let's see what happens when the food coloring beads are pushed into the water and just kind of press through with the stirring rod. So even mixing them around, it didn't spread into the oil. The second the food coloring goes into the water, it spreads right apart and mixes in very easily. So based on what you've just seen, oil and water don't mix. Water, we know from bonding, is polar. Oil is nonpolar. Food coloring mixes into the water very easily. Food coloring does not mix into the oil. And even with stirring, you could see the beads of food coloring just stayed together. The second the food coloring was pushed through the oil layer into the water, the food coloring instantly mixed into the water. So based on what you've seen, the food coloring mixes into the water. The food coloring does not mix into the oil. What do you predict the polarity of the food coloring is? We know water is polar and oil is nonpolar. Based on the mixing you've seen, what should the polarity of the food coloring be? Right? It should be polar because like dissolves like. Okay. So when substances do mix together, like the water and food coloring, we call them miscible. They dissolve and mix. When substances do not mix together, they're called immiscible. And I wonder if I can't move my slide bar. So when it's immiscible or insoluble, it does not dissolve. It will not mix. That means they have a different polarity. So in order for a substance to form a solution, or two substances to form a solution, they have to be able to dissolve in the first place. Like food coloring and oil will never form a solution because they just don't mix. So to form a solution, the solute must dissolve in the solvent. A solution is a homogeneous mixture of substances behaving in the same physical state. Does not always have to be a liquid that has a solid dissolved into it. It can be gases, it could be two liquids that mix together. A solution means one thing dissolved in the other fully, and you can no longer see it, it's no longer visible, it's a homogeneous mixture. The solute is always the component that dissolves into the solvent. The solvent is the big medium that dissolves the solute. So you kind of define these two terms using the words in each other. So each word is part of the other's definition. So salt water is a common solution. So thinking about when you make salt water, you sprinkle your salt into the water. Which do you predict would be the solute and which would be the solvent? Right? So in aqueous NaCl, which part is the solute and which part is the solvent? Okay. So the solute's the salt, the solvent is the water, right? And that's been just kind of defined with the picture. All right, so properties of the solution. Solutions are homogeneous. That means you can only see one component. It looks like one component. It looks like a pure substance, but there are more than two components mixed. They're clear. That means transparent. That does not mean colorless. So my green water, that is a solution. It has color, but it is still clear and transparent. If I had a laser pointer, I could shine it through and you would see the light passes right through. I don't, unfortunately. You should remember from the beginning of the year, the mini lab we did that showed homogeneous versus heterogeneous mixtures. The laser pointer pointed right through that salt water. They will not settle upon standing. So this food coloring in my water, this green water, will stay that way forever, essentially. And if I was to pour this through filter paper, green water would pass right through. Can you think of some common things that you might encounter every day that are solutions? Think about things that you might drink. So, soda. If you make yourself iced tea, I made myself iced tea yesterday, like just the powdered mix. Real iced tea, just using a tea bag. Right? Salt water, sugar water, coffee. These are all examples of solutions that you can encounter every day. And again, it doesn't always have to be a solid dissolving into a liquid. It can be a gaseous mixture, the air that we breathe and that we live in. That's a mixture. You've got oxygen, argon, nitrogen, water vapor, trace elements, carbon dioxide gas, all floating around. You can't detect them. You can't see them. It looks like just one substance. That's a homogeneous mixture. That is a solution. All right, so factors that affect solubility. So there's polarity, which we just discussed. If something will dissolve or not is based on if they have this like polarity or not. Temperature can affect solubility and pressure. So there's a reference table that shows this, table G. So hopefully you all have your reference tables. If you don't, you can go ahead and print them out. The link is on my website. You can also just Google New York State chemistry reference tables. A PDF will pop up. You can print it out just to make sure you have your own copy. So temperature and table G. Well, table G shows you all of these different substances at different temperatures, how soluble they are when dissolved in 100 grams of water. As the temperature increases, the solubility of a solid will increase, right? So when you increase temperature, you get more movement, more kinetic energy, and a solid dissolving into a solution will become more soluble, right? That's why if you put sugar in your coffee, it dissolves more quickly in hot coffee than when you put it into iced coffee. Iced coffee, it takes a little more time. If you're getting iced coffee and you put sugar in it, like solid sugar, you'll notice you just have the sugar that sits on the bottom. And if you're using a straw, you'll kind of sometimes slurp up the sugar. It's a little gross. It doesn't dissolve in the iced coffee as much as it will in the hot coffee because temperature increases the solubility of a solid. Now, if you go to the opposite end, as temperature increases, the solubility of a gas will decrease because the particles move faster and a gas will then escape. So if you think about soda, we drink soda when it's cold because it keeps it more carbonated. It keeps the carbon dioxide gas in more easily. It keeps that gas more dissolved. So using your table G, I would like you to record all substances that increase in solubility as the temperature increases. And then once you've done that, are these substances solid or gas? So that's what I want you to kind of label down. All of the substances on this table that increase their solubility when temperature goes up. And then I also want you to indicate if it's a solid or a gas. And when you've done that, you can go ahead, you can pause the video to do that. Let's see if you were right. And there you go. You could see everything that increased as the temperature increased was a solid. And the substances, there's 3 of them that got less soluble when temperature went up. Those were gases. So I want you to think about this. Why does soda become flat when it gets warm, if it sits out? And based on the answer to that first question, does gas solubility increase or decrease when temperature increases? So I want you to come up with your answers to that. And as temperature goes up, carbon dioxide molecules move faster and escape the solution more easily. That's why when soda is sitting out, the gas that's in it, CO2, it's just going to escape. And that means that when the soda warms up, the temperature was going up, gas becomes less soluble as temperature increases. Well, pressure doesn't affect solid solubility. It doesn't matter what the pressure is on the surface of a liquid. It's not going to affect a solid. It's only going to affect a gas. So, why does pressure increasing cause the gas to become more soluble? So you could see here, there's a piston that simulates an increase in pressure, and it kind of pushes down on the gas molecules. So why does increasing pressure cause a gas to become more soluble in solution? Think about what happens. Well, if you increase the pressure, you're going to just push the gas molecules in, and that causes the gas to become more soluble. So soda, it's canned and it's sealed and it's under high pressure. That's why if you ever shake up a can of soda or a bottle and open it, all of the gas escapes rapidly because it was under high pressure. And when you remove all of the gas from the solution and you open it, it escapes instantly. So usually if you drop a can of soda or a bottle, you have to let it settle back down and let the pressure stabilize again because you need that high pressure to keep the gases dissolved and keep them forced in solution. And that's it. So I hope that you were able to pause the video, take your notes, use these notes to help you answer the questions that I've attached to the assignment as well. I hope everyone's doing well. Hopefully we get to see each other again by the end of the year. At this point, we're closed until May 15th. I don't know when school's going to open up again. Your guess is the same as mine. It would be nice to kind of get in the classroom again and see everybody before the year is out. If you have any questions, feel free to email me, use Remind. And again, every Thursday at 4 o'clock is when I want to try and do live sessions. So if you want to log in just to chat, if you have any extra help questions, general questions, we'll be there. Okay? Bye.